Last class, we left off, we were learning about significant figures and how to use them in calculations. A lot of the time, we will not be switching up our operations. It will come up occasionally. When we are switching between operations, that's when we tend to run into the most trouble. So like C and D, we've got both multiplication, division, and addition, or just multiplication and addition. And so when we're switching between steps, we need to consider what's the thing we care about, or what's the thing that we are counting for that particular operand, the operation. So our rule for multiplication and division, as a reminder, we're going with which term has the fewest significant figures. So if one of our terms has 3 and the other has 5, our final answer gets rounded to 3 significant figures. If we're doing addition and subtraction, what we care about is decimal places, and we are going to use the fewest number of decimal places in our final answer. So like in this left example, we're adding all these terms up. We've got 4, 2, and 3 decimal places. 2 is the smallest number of decimal places, and so that's the number we'll round to for our answer. Some other terms relevant to taking measurements are precision and accuracy. And precision and accuracy are often confusing even for people that teach precision and accuracy. Because a lot of the time in our normal conversations, our non-scientific conversations, we would probably think of precision and accuracy as being sort of the same thing, and they're not. Accuracy, or accurate, right, refers to how close the measured value is to the actual value. Is it close to what it's supposed to be? Accurate / on point. It hit the target. Precision, on the other hand, refers to how close a series of measurements are to one another, or how reproducible they are. So precision is more like consistency. So sometimes you can be accurate but not precise. You can also be precise but not accurate. It's also possible to be both. And the fourth option is to be neither accurate nor precise. Ideally, we are both accurate and precise, especially in our measurements. So we're going to look at a couple of trials. 3 students, they repeatedly weighed a lead block. We know that the true mass of the lead block is 10.00 grams. Presumably we bought it from a scientific manufacturer and they measured it with their calibrated instrumentation, and they told us, hey, this is a 10-gram lead block. So students A, B, and C took their 4 trials. They also found an average, and we're going to look at their data graphically on the next slide. So student A, this is their data. We've got our mass on the y-axis. So higher up is more mass, lower down is less mass. We're kind of zoomed in on the area that we care about, which is around 10 grams, since that's the true mass of the weight. And then our trial numbers is the different bars spread out here on the x-axis. So student A is both inaccurate and imprecise. So we've got values that are a fair bit above, we've got values that are a fair bit below, and they're not very consistent either. So they're all over the place, so they're imprecise, and they are not close to the true mass, generally. So they're also inaccurate. So that imprecise, there's a big spread between them. The inaccurate part, not all that close to 10. And inaccurate and imprecise are kind of qualitative terms, and so it sort of depends what your metric is, like what your basis is for being inaccurate or imprecise. In some other contexts, being off by 0.49 grams would be a really quite good measurement. Like if we were measuring the mass of a car and we were off by half a gram, I would say that that's a really good measurement. In this context, because it's 10 grams, it's not quite as good. Student B, their data, notice that all of their data is below that 10-gram true value. But despite being off target, being inaccurate, despite being off target, they are still very consistent in how far their measurements are from each other. So they did a good job keeping their measurements close to each other. It's just that they were all a little bit below what they were supposed to be. This would be sort of like if you're helping out with cooking a dish and somebody tells you, hey, cut these carrots up into half-inch slices, and you cut one piece, and you measure all the next pieces with that same carrot slice. Maybe they're all an inch, but you cut them all to 1 inch exactly. That would also be an example of being precise but inaccurate. They're all really nice and repetitive. You just had the wrong measurement to begin with. And then student C did everything correctly. So their average value is right around 10 grams, and they're all pretty closely spaced together. So ideally, we would like to be more like student C. Occasionally, some science procedures and experiments, it's okay to be like student B, have precise measurements, because there are experimental ways that we can adjust for being inaccurate, as long as we're precise. The results of student A, that's the one where they're both inaccurate and imprecise. So they're off target and they're not very consistent. Shows some random error. I mean, they all show some random error. But random error, one of the types of error, this is essentially uncontrollable error. It's something that's out of our hands. There's always going to be a little bit of plus or minus for whatever reason. It's an error that has equal probability of being too high or too low. One of the ways that we get rid of or minimize our random error is by taking a lot of measurements. So if you take 5 measurements and some of them are randomly going to be high, some of them are randomly going to be low, those random high and low values will cancel each other out to some extent when you average them. And so we can reduce our random error by taking an average. Student B here has inaccurate values, but they are precise. They're all right around each other, and this is a sign of a systematic error. So a systematic error would be something that we do, usually, or something that our instrumentation is set up to do, from being set up incorrectly, that's always going to be a little bit too low or a little bit too high. This would be like if we were told to measure out, if somebody said, hey, we're cutting firewood for some reason, hey, cut this long tree that I've cut down that fell in our yard, cut that down into 1 yard lengths, and we pull out a big meter stick and we measure it in meters. We cut all of them down into meter-sized sticks. We just used the wrong measurement, so we probably got about the same length every time, but because we were using the wrong stick, they all ended up being too long. Something along those lines. And there are ways of avoiding or accounting for systematic errors. And then student C shows little systematic error and maybe a little bit of random error, but definitely a lot less than student A. So ideally, we'd like to be like student C. Questions about precision and accuracy? Cool. All right, on to a very brief talk about energy. Energy is the capacity to do work. So if you wake up in the morning and you're feeling energized, that usually means you feel like you can go out and do stuff that day. Whether that carries with you through getting out of bed, who knows? So you wake up with a lot of energy, you've got a lot of capacity to do work. Work is action over distance, or force over a distance, which can make some funny definitional issues. So for example, we've got this person in their hard hat pushing this really large box, and it looks like a cardboard box, which is crazy. So they're pushing that cardboard box across the floor, and because they're pushing on it and it's moving, they are doing work. One of the weird ways where you can definitely spend your energy, but you're not doing any work, right, is if I get up against the wall, like pushing on the wall obviously not really going to move. I'm not going to shift the whole building because we're in the building. I can push on this all day long, and technically, because it hasn't gone anywhere, I haven't done any work. But I would definitely be tired after a long day of 12 hours of pushing on the wall, assuming I was trying very hard at all. That's more just like a weird thing. So there is motion required for it to count as work. Walking is work because you're moving your body over a distance, and it takes energy to be able to do work. There are several types of energy. Here's 3 of them. Our first type of energy is kinetic energy, and this is the energy associated with motion. So rolling across the classroom, which is more fun when there's not carpet because you roll farther. But rolling across the room in a rolly chair, or spinning in a chair, or walking, driving your car, riding the bus, those are all going to be kinetic energy. Kinetic energy is movement energy. Energy in motion. We also have potential energy. Basically could turn into another form of energy. There are different types of potential energy. One of the ones that we often think about is like gravitational potential energy. So if you lift something up really high, like the picture of the 10 kilogram weight, the 22 pound weight that's on the building, if you lift something up high and then you just let it fall, that would be turning the potential energy, gravitational potential energy, into kinetic energy. And then if it hits the ground, it releases that energy somehow. Like if it's not a really solid weight, it might be that the weight blows up into a bunch of different pieces, as would happen if it was like made of glass. It could also turn into thermal energy, so it could get really hot. That also can happen if you like bang things together. And thermal energy is essentially heat energy, temperature energy. We can measure thermal energy with a thermometer. Thermal energy is actually a type of kinetic energy. It's the result of the little particles, like atoms and molecules, like vibrating in different ways. It's the amount of energy that those have moving around, shaking in their place. Or in the case of gases, actually flying around. Other types of energy include chemical potential energy, which I thought was going to be on the next slide. There's also chemical potential energy. So some chemicals, because of the way that they are, have a lot of stored energy. It's sort of like springs or rubber bands. Like if I stretch a rubber band, I don't have one. I'm not taking the one out of my hair. If I stretch a rubber band out, you can do like the finger gun thing with rubber bands, right? You're stretching it out, you're putting energy in, storing it, and then you release that potential energy and it goes flying as kinetic energy. Chemical material can also hold energy in that way. So like TNT, other explosives, have a lot of strain and stress in the way that they are held. It's sort of like stretching out that rubber band. They're always in that position. If you give them the opportunity, a little bit of a spark, boom, they explode and they release all of that energy. We have a law of conservation of energy. Does anyone remember the other law of conservation that we've talked about? I'm pretty sure that was this class. Law of conservation of mass. So mass or matter is neither created nor destroyed, and the same is true generally for energy. So the law of conservation of energy says energy is neither created nor destroyed. So we're not going to make new energy, we're not going to destroy energy. We're going to transfer it, or it can be transferred from one form to another, like the potential energy turning into kinetic energy, and then maybe the potential or the kinetic energy turns into thermal energy, which is less easy to see sometimes. But the total amount of energy is going to be constant. Things with high potential energy tend to be unstable. Think of children. I was going to say a different thing, but think of little kids that like are on a sugar rush, right? Sugar high. They've got a lot of energy. If you try to get a child with a lot of energy to sit still, chances are they will not be happy with that. They'll do lots of fidgeting in their seat. They'll maybe decide they're not going to sit there and they're actually going to run around instead, or all sorts of other possible outcomes. Similarly, chemicals, oh look, there it is, chemical potential energy. Chemicals can also have really high potential energy, which causes them to be unstable. There are certain shapes that tend to be really unstable, which we'll talk about more when we get to Lewis structures much later in the class, or moderately later in the class. Chemical potential energy is an electrostatic force energy, can be because of charged particles. It just depends on how you define it. So summary, energy is always conserved, maintained, same amount of energy in a physical or a chemical change. We don't create or destroy it. Systems with high potential energy tend to change in a way that lowers their potential energy, often releasing energy into the surroundings, like a rock rolling down a hill. We will talk a little bit, I think, more about high potential energy changing to low potential energy. One way that we take advantage of chemical potential energy is most vehicles, all internal combustion engine vehicles, are burning some sort of fuel. There's energy in the bonds in octane and other chemicals that are in our gasoline, and we can burn those to produce kinetic energy in our engine block that gets our cars, our buses, our other forms of transportation to move forward. Okay, and now we'll see how distracted I get talking about the units of measurement, because they're really cool. So a little bit of background for part of one reason that we could say that units are important. In 1999, NASA lost the $125 million Mars Climate Orbiter. This is, I think, a representation of it. It might be a picture, I don't know. But this thing descended a little bit too far into the atmosphere, which means it picked up more friction, and that friction was more than it was designed to handle, and it burned up. Crispy chunk of metal sent to Mars. And when they investigated, the chairman said the root cause of the loss of the spacecraft was a failed translation of English units, the ones we use, into metric units, the ones basically the rest of the world uses. So somebody put in the wrong units somewhere, or they wrote the code so that it was in the wrong units, and boom, $125 million gone. And lots of time and work and other things, of course. So units can be really important. It's important that we know what units we're dealing with. It's important that we convert our units correctly. And chemists love units. We use units all the time. The two most common unit systems are going to be the metric system, used in most of the world, and then the English system, used in the United States, and I think parts of the UK. Not that that's really important, but it's basically just two countries that use English units, and all of the scientists in those countries basically use the metric system. So most of the world uses the metric system. It's important that we learn the metric system to be able to communicate with people around the world about units. Scientists use the International System of Units, and you might notice that this abbreviation, SI, is backwards, and that is because it comes from the French, which is written here. So system, the word for system and the word for international are flipped, and so that's why it's SI units instead of IS units. Some of the base units that we use in the SI system are shown here, and ones that you don't really need to know that much about, at least for this class, I'm canceling through, crossing through. So different quantities, things that you can measure: length, mass, time, temperature, amount of a substance, and then the various units that we use. So these are the base units: meter, kilogram, not the gram, second, Kelvin, mole, and then some of the symbols. A lot of the time for temperature, we report it in degrees Celsius rather than Kelvin, but it just depends on the context. You should know the unit symbols. So like all of these symbols and a bunch of other metric prefixes, you will want to have memorized to know what they mean, because oftentimes we'll just see them as their abbreviated form, and you need to know what those abbreviated forms mean. All right, our unit of length. The SI unit of length is the meter. It's a little bit longer than a yard. So if we look, here's a meter stick, here's a yardstick. Those are probably about to scale. If you take a 100-yard football field, it's only 91.4 meters. So a meter slightly longer than a yard. I think it's like 3.3 feet or something, and a yard is 3 feet. Tall people are more in the vicinity of 2 meters tall. 2 meters is taller than 6 feet. A lot of these, all of these? I think all of these are based on some universal constant, except for maybe the mole, because that's just counting. So the meter, the way that the meter is defined is actually based on the speed of light and how fast it travels in a vacuum, which is important because then, since that's always the same, you can measure it anywhere in the world, as one does, and figure out exactly what a meter is. We've got a universal reference point, rather than, say, having like one stick somewhere in a museum, probably in England is where it would be, or like Switzerland, having like one stick and everyone's like, this is the stick that's 1 meter. It's a little bit inconvenient if you want to like check your references and you have to go to the original stick and make sure that you don't touch it in any bad way, because then that would make the meter stick shorter. So it's a better system having universal constants. The kilogram measures the mass of an object. And 1 kilogram is about 2.2 pounds. Somebody who weighs 130 pounds would be a little shy of 60 kilograms. And the kilogram, being a unit of mass, is slightly different. It's definitionally different from pounds. So pounds measures weight. And weight is a measure of gravitational pull on matter. We are generally in this class going to assume that all of the things that we're doing are on Earth, and we're not going to take into account slight gravitational fluctuations, because the gravity is a little bit different here than it would be somewhere closer to the equator, versus if you're really high on a mountain. The differences aren't significant, though, for our purposes. Weight also depends on where you are, right, because of the gravitational pull. So if you send a 130-pound person from Earth to the moon, it's the most expensive, fastest miracle weight loss program you've ever seen. Now they only weigh 21.5 pounds. And it only costs millions of dollars, right, if we wanted to do that. However, if you switch the scale to kilograms, guess what? The person's mass is the same. So it's the same amount of person, right? If you send a person from Earth to the moon, it's the same person. They've maybe lost a little bit of weight, a little bit of mass, but it's the same person. They haven't magically shrunk to 1/6 of their size just because you stuck them on the moon. Another one that we often use is the gram. 1 gram is 1,000th of a kilogram. That's too many ones. Or 1,000 grams equals 1 kilogram. A nickel, our 5-cent piece, has a mass of about 5 grams. So grams are relatively small compared to kilograms, but kilograms is our base unit. The kilogram used to be based on like a little sphere of metal that somebody had in basically a museum. Cylinder, not sphere. Yeah, little cylinder of metal, and they kept it under like multiple domes for protection and like in a vacuum. And then there were like replicas that were made and sent out all over the world. But it's now based on a universal constant, the Planck constant, which is cool. Look up Kibble balance, Kibble balance, if you want to know more about that. And we also have our SI unit of time, which fortunately for us, it's the same one that we're used to. So time all around the world in every system, as far as I know, is also measured in seconds. It was originally defined as in terms of days and years, but now it's based on this many periods of radiation emitted from a cesium-133 atom. So they've got atomic clocks that can measure the number of amounts of radiation that's emitted from this cesium-133 atom. And then they just broadcast that signal of like their official timekeeping record. They just broadcast that all over the world. So like when I was a kid, it was a really cool thing. We got a VCR. So we got a VCR player, and it had something about atomic clock on it. And so it would connect over radio waves and like automatically update the time. So if the power went out in your house, it would come back on after a few seconds. Boom, it's got the correct time on there. You never had to go and reset it because of power outages or just like getting off a little bit. Most of us probably have had the experience of looking at different clocks in our house or wherever we live, or like in our car versus our phone. And it's like, oh, now my car is 2 minutes fast, but it used to be 4 minutes fast. And that's all because the internal timekeeping mechanism is just off by a little bit. So over long periods of time, they start to diverge. Eventually, if we didn't ever correct our time relative to like one source, we could be off by hours or days. And then it would be pretty hard to figure out when to be what place when. And where? No, we'd have where. That'd be fine. So it's great that we've got a universal time keeper, a constant somewhere in the world, and our phones automatically update with that. Our SI unit of temperature, how hot something is Kelvin. Other units of temperature that you might know of, the other two big ones, degrees Fahrenheit and degrees Celsius. Kelvin does not have degrees. It's just kelvins. So there's no, that little 0 in the top left corner. We don't have a degree sign in there. It's just Kelvin. Temperature is a measure of kinetic energy. From those atoms/molecules moving. If you cool things down, those atoms and molecules do less wiggling and jiggling and moving around. And eventually you can get down to 0 Kelvin, which is where, in theory, the atoms and molecules are not wiggling or jiggling. They're just completely frozen in place. Temperature also affects the flow of thermal energy transfer, what we call heat. Heat moves from hot to cold. So really hot objects, if you heat up a cast iron skillet on the stove and you like put your hands near it, you can feel, even after you've turned the burner off, you can feel the heat coming off of it. It's radiating heat, and that's going to you because you're colder, and so it warms you up a little bit. Same as fires and other hot things. Okay, so some of those temperature scales. We have the Fahrenheit scale, which has units of degrees Fahrenheit. That's typically what we use. 0 degrees Fahrenheit apparently was because of saturated salt water having a temperature of 0 degrees Fahrenheit for its freezing point. 96 degrees Fahrenheit, somewhere in that range, is normal body temperature. The Celsius scale is used by most scientists, lots of scientists, and most other countries. So pure water freezes at 0 Celsius. And boils at 100 Celsius. And I know that I'm writing that right next to what it says in the slides, but it's easier to find it if I wrote it in red than if you're just scanning through the text. You should know that water freezes at 0 degrees Celsius and that it boils at 100 degrees Celsius. Both these temperature scales can go into the negatives. One way that I've heard the Fahrenheit scale described is that the Fahrenheit scale is how we as humans feel. So 0 degrees is super, super cold. 100 degrees is pretty warm or hot even. And the Celsius scale is how water feels. So at 0 degrees Celsius, water is freezing cold. At 100 degrees Celsius, water is boiling hot.
So what temperature does water freeze at without salt water?
In Fahrenheit?
Yeah.
32.
Oh.
And then it boils at 212 Fahrenheit,
Okay.
which is a less convenient scale than Celsius, where it's just 0 to 100. 32 to 212 is not as nice. There is a temperature in which Fahrenheit and Celsius are the same. Does anyone know? Just, it's a fun fact, and that's all it is. Does anyone know when Fahrenheit and Celsius are the same? What temperature that is? Cool, I didn't expect anyone to, but I just thought maybe. So minus 40 degrees Fahrenheit is the same as minus 40 degrees Celsius. It's the same in both temperature scales. And the Kelvin scale sets 0 as the lowest temperature, so you can't have negative. So if you say it's minus 40 outside, they should know you're talking about Fahrenheit or Celsius, and either way, you're right. And they shouldn't guess that it's Kelvin, because that doesn't go negative. Some other things that I'd like to point out about temperature, because I think they're interesting. Notice that our freezing temperature here for water to our boiling point for water is 100 degrees Celsius. It's also 100 kelvins. So that means kelvins are the same size as degrees Celsius. So if you increase the temperature by 1 degree Celsius, you're also increasing it by 1 Kelvin. Our Fahrenheit scale, though, if we go from water freezing to water boiling, is 180 degrees Fahrenheit. So our degrees Fahrenheit are smaller than our degrees Celsius. And there's also a difference in our freezing points for Celsius and Fahrenheit of 32 degrees. I'm pointing out those two particular things because I'm pretty sure the next slide has our conversions. It's the next slide. Kelvin scale assigns 0K to absolute 0. So 0 Kelvin, if it's reachable, nobody's done it yet. If it's reachable, in theory, there's no motion at all. So far, they haven't gotten to 0 Kelvin, but they've gotten really darn close. And weird things happen down there. Okay, temperature conversions. We'll need to know how to convert temperature from Celsius to Fahrenheit, from Celsius to Kelvin, from Fahrenheit to Celsius, from Fahrenheit to Kelvin. All of the possible ways, we need to know how to do them. And these are our two formulas. This is one way that you might see them. Typically, if you're given a temperature conversion formula, I'll give you one form of it. And if you want to work it the opposite direction, you have to know how to do the algebra to switch it around. So both of these temperature conversions, this top one, is designed to go from Fahrenheit to Celsius, because Celsius is by itself. So we can find Celsius if we're given Fahrenheit. The bottom one, we can put in degrees Celsius and we'll get out Kelvin. If we wanted to work the opposite direction, we have to do a little bit of algebra. The 32 that I pointed out, the difference between where water freezes, shows up in our Celsius and Fahrenheit conversion. It's this 32 here. And this 1.8 is because of the difference in the size of the degrees. So 180 Fahrenheit degrees versus 100 degrees. There's a factor of 1.8 in there if you take the 180 divided by 100. So that's where this 1.8 shows up, because we're accounting for the difference in the size of the degrees. Okay, let's do some conversions. And I'm going to assume that we've probably already done this before, so I'm just going to let you try it. And I'm leaving the formulas up there for you. So gallium is a solid metal at room temperature, but it will melt to a liquid in your hand. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on A, the Celsius scale, and B, the Kelvin scale? Okay, a couple of temperature conversions. So we were trying to convert 85.6 Fahrenheit. We want to convert it to both Celsius and then Kelvin. Since we are trying to find Celsius, we have our formula set up already in the correct way. Degrees Celsius is by itself. It's just on a side by itself, and it's in the numerator. So that means that we are solving for degrees C. We just have to plug in what our degrees Fahrenheit is. So for A, we are doing degrees Celsius equals degrees Fahrenheit. We were given a value of 85.6. And the formula says subtract 32. It's a weird 3. And then we divide by 1.8. And you should get out 29.7, and that 7 seems to repeat. So we put a line over it. That means that 7's repeating forever, allegedly, apparently. That would be our degrees Celsius. And we'd probably round it to 1 decimal place. So it'd be maybe 29.8 degrees Celsius. And then we need to convert our temperature. We should use the one with the repeating 7. We need to convert our temperature into Kelvin. Conveniently for us, it's already set up the way that we have it up here. It's already set up to convert to Kelvin. So for B, we're plugging in for Kelvin. It's equal to our degrees Celsius, the 29.7 repeating. Then we add to it 273.15. And we should get out 302.92, and then that 7 repeating shows up again with units of Kelvin. We'd probably also round this to 302.9 Kelvin. So we've got 1 decimal place. Questions? The one place where I think people are likely to make a mistake, most likely to make a mistake with this problem, is the degrees Celsius. If you don't do this subtraction step in parentheses or by itself, and then you divide by 1.8, you will get the wrong answer. So for example, let me write that this is wrong. Wrong version. If you put into your calculator 85.6 minus 32 divided by 1.8, you will get something that is not correct. And that something is 67.82 repeating degrees Celsius. The reason this is wrong is your calculator is going to do the division before it does subtraction. So it does 32 divided by 1.8, and then it subtracts that from 85.6.
When you're doing the sig figs, when you're okay, so when you do the whole math and everything, and you're trying to write down the answer,
Yeah.
and you're counting the sig figs because you're doing division, because when it comes out, it goes there's 3, 2, 2 sig figs, but the answer comes out to 3 sig figs.
So 85.6. We subtract 32. It's a conversion. I'm assuming that the 32 is exact. Okay. So it's not going to affect our significant figures. Okay. It's not going to affect our decimal place either. So we do 85.6 minus 32. It'll give us something that's got 2 digits in front, and we'll still have that 0.6. So we'd have 3 significant figures. Okay. We divide it by 1.8. I'm assuming that's also exact. So that's not going to affect our significant figures either. So we had 3 going in. We have 3 coming out.
I thought it was the lowest.
Right, but the 1.8 is exact. The 32
Oh, okay.
probably also exact.
Okay.
Okay, let's do it in the opposite direction, just for fun. Let's say that we're talking to somebody in Italy, and they say it's boiling hot out here. Not literally, but they say that it's 47°C outside, and that's just unbearably hot. What would that be in degrees Fahrenheit? We had degrees C equals degrees Fahrenheit minus 32 over 1.8. This is another place where I see people possibly running into trouble because we've got 2 algebra steps, which is not crazy, but you have to do them in the correct order. If you do them in the wrong order, you get the wrong answer because you did the math wrong. So to solve this equation, we're trying to find degrees Fahrenheit. So we need degrees Fahrenheit by itself, and it has to be in the numerator. That means that we have to move the 32 over. We also have to move the 1.8 over to be with the degrees Celsius. Which one do we do first? Do we remove the 1.8 or do we move the 32?
1.8 and divide.
We have to move the 1.8. To move the 1.8, we can treat both sides equally, multiply both sides by 1.8. When we do that, the 1.8 on the right side cancels out, and it would turn into 1.8 times degrees Celsius equals degrees Fahrenheit minus 32. And then we can go ahead and add 32 to both sides. That will get rid of the 32 on the right side. And now degrees Fahrenheit is by itself. Flipping it left and right, we'd get degrees Fahrenheit equals 1.8 times degrees Celsius plus 32. And we don't need any parentheses for this because our calculator will do the multiplication first automatically. So we would plug in our 47 degrees Celsius where we have degrees Celsius here. So 1.8 times 47, add 32. It is truly, indeed, boiling hot out there. I think even we would be appalled because it's 117 degrees Fahrenheit outside, and even around here, that's just too hot to exist outside. Questions? Yeah.
Where did you get the 47 Celsius from?
I made it up.
Oh, okay.
Other questions? Said bonus. So it's separate. Cool. We will also be using, since we're using the SI system, we're using the metric system, we're going to be using prefix multipliers. So scientific notation lets us express really, really big numbers, which we have to express sometimes, and really, really small numbers, tiny numbers, and they let us do so in a compact manner. So when we're dealing with astronomically large numbers, like the number of particles or the number of atoms in like even something as small as like a calculator or a penny, we're dealing with potentially 20 to 30 place values. And that's really uncomfortable. If we have to write out that many zeros, we're likely to lose count. I probably would. It's also just, it takes way too long, and so we get to use scientific notation instead. And the way that we get around this when we're talking about units is for our SI and metric systems, we can use prefix multipliers, seen on this slide coming, to adjust our standard units. And the multipliers change the value by powers of 10. Basically, they just move the decimal place. And this is really nice for a bunch of reasons. One of the reasons this is really nice using prefix multipliers, we use the same set of prefix multipliers for all of our units. So our meters use the same prefix multipliers. Grams and kilograms, same prefix multipliers. We can even use them for seconds. We can use them for pretty much anything that you would want to. And it's always going to be increments of 10 or 1,000, something like that. As opposed to our beloved English system. And in an English system, how many inches are in a feet? A foot? 12 inches in a foot. How many feet are in a yard? 3. That's a different number. How many feet are in a mile? 5,280, which is a third different number. How many ounces are in a pound? 16. How many ounces are in a cup?
16.
8.
8. Oh.
So those are different numbers, right, from even the ones that we were using before. How many cups are in a pint?
4.
2 cups in a pint.
Oh, 2.
How many cups are in a quart? 4. How many quarts are in a gallon? Also 4. Right, so all these different units, all these different conversions, and that's just like the standard ones that we're used to using. There's other weird English system units like furlongs, which is the distance around a racehorse track. And like there's different versions of miles and tons, and there's all sorts of crazy stuff. And when we're working in the SI system, we just use, bam, all of these prefixes, and they're all different just by factors of 10. So we're just moving the decimal place over one direction or the other. We're multiplying by 10 to the minus 3, 10 to the minus 12, 10 to the 3, 10 to the 2, other stuff like that. So we just learn one set, and the way that my brain learned them, the way that I think about them, I'll talk about in a second. There's some that we're not going to really use, like deci. We're not really going to use, and we probably won't get to these big ones either, like exa or peta. We probably won't use some of these small ones, like femto or atto. We probably won't even use pico. The rest of them, it would be good for us to know. So we should know these prefixes. Fortunately for us, we are probably already, at least in terms of like hearing them and like knowing, oh, that's a thing, I recognize that. We're probably already familiar with about half of these or more. So if you have a digital device and you're familiar with the amount of information that it can hold in any sort of way, right? You're probably familiar with tera, like terabytes, giga, like gigabytes. Gigabytes would be like games or movies would take up gigabytes. Megabytes is going to be more like a picture file. Kilobytes is like a PDF file, maybe a Word doc, other things like that. So these kilo, mega, giga, tera, we already use those to describe the amount of storage that like our phone or our laptop or our flash drive can hold. And then centi, like centipede, centipedes allegedly have 100 legs. So centi meaning 100th, like cent. Or penny, there's 100 of those in a dollar. So it's 100th. A cent is 100th of a dollar. And then milli, micro, and nano being our other small units. Aside from centi and deci, which I've crossed out, and there's some other ones in there, I'd like to point our attention to the multiplier that we're using. So for kilo, it's 10 to the 3. The next multiplier above that, add 3, 10 to the 6. The next prefix above that, giga, add another 3, it's now 10 to the 9. Moving from giga to tera, it's 10 to the 12. So other than the first couple of ones around our 1, our reference frame like meter, other than those, we're increasing in orders of magnitude of 3. And it works in the opposite direction as well. So for a milli, it's 10 to the minus 3. Micro is next in line. It's 10 to the minus 6. Nano is smaller than that. It's 10 to the minus 9. So if you can remember that they're spaced out by units of 3, and you remember what direction we're counting, so if you remember kilo, mega, giga, tera, You can just count in your head, how many times did I go up? Okay, add 3, add 3, add 3. And then that might help with remembering them. That's the way that I learned them initially. Add 3 to the exponent. And the same for the opposite side. Subtract 3 from the exponent. Just in the opposite direction. So milli, micro, nano. One weird one in here, micro gets the symbol mu, which is the Greek letter. It's got the little like front tail. And one other one that I'd like to point out is that mega is capital M. Milli is lowercase m. So it is important that we correctly use uppercase or lowercase. A lot of food and beverage is not so careful about this. See something that I think is funny. So you like go and buy a drink and it's like 1,000 capital M capital L. This is not 1,000 megaliters because I can hold it in my hand. You meant 1,000 milliliters. So that's just something that I laugh about to myself when I'm in the grocery store. So questions about any of our prefixes? Cool. All right, let's do some practice with conversions. I think we will talk about this a little bit later. But generally, the way that we can use these prefixes, the prefix, the symbol, stands for or is equal to whatever the number is. So giga is equal to 1 billion. Mega is equal to 1 million. Kilo is equal to 1,000. So anywhere you see one of those, you can substitute in the number. Substitute number for the prefix. So for example, 4.5 megameters, crazy distance. 4.5 megameters, we're going to substitute in what mega is equal to. Mega from our prefix table is equal to million. So mega equals million, which is 1 with 6 zeros after it. So we're going to plug in 1 million in the place of that mega. So 4.5, we plug in the million. And that's now in meters because we got rid of the mega. So it would be 4,500,000 meters. There are other ways that we can make conversion factors and use them, which we'll get to probably next week, Monday. This is one way that we can use these prefixes. And we'll use the same strategy when we're coming up with the conversion factors. Say that we've got this number of liters, 7.13 times 10 to the minus 9 liters. We want to figure out how many nanoliters that is. So we'd find nano on our prefix table. Nano is equal to 10 to the minus 9. So we got 7.13 times 10 to the minus 9, very convenient. Liters equals how many nanoliters? Well, nano is equal to 10 to the minus 9. And so in place of this 10 to the minus 9, because nano is equal to 10 to the minus 9, we can plug in the nano prefix instead of this 10 to the minus 9. So it would just be 7.13 nanoliters. Because we're swapping in the nano for the 10 to the minus 9. Usually it doesn't work out quite this nice and neatly, so we'd have to use a conversion factor approach instead. But this expressing something as 7.13 nanoliters is a little bit more convenient than 7.13 times 10 to the minus 9 liters. There are other units that are derived units. Some of our volume units, many of our volume units are derived units. So derived meaning it came from something else. So derived units are from other units. They're built out of other units. They're like combo units. So things like miles per hour and meters per second are other derived units. We're combining miles and hours, or meters and seconds. We're putting those together to make some other units. Volume, which is a measure of space, 3 dimensions, can also have derived units. Any of our units of length, if you cube it, if you take it to the third power, becomes a volume unit. So things like cubic meters, cubic millimeters, cubic centimeters, cubic inches, cubic feet, other things like that would be examples of derived units for volume. We also have some volume units that aren't derived, and those are the liter and the milliliter, which we will be using quite a bit. Liter, 1 liter is similar to, but not the same as, 1 quart. So you can buy the big plastic bottle of like Pepsi or Coke or Dr. Pepper or whatever you drink, right? If you drink soda. Usually those come in a 2 liter container. Those are similar-ish to 1 quart. And the person sitting in the box here, this is a 1 meter by 1 meter by 1 meter cube. And that's my mother sitting in a box. It's like a science museum, so you could like sit in the thing and then have your picture taken, and you kind of like feel what 1 cubic meter feels like. So it's a relatively large amount of space. You could probably fit at least 1 more person in there, not too uncomfortably. Okay, our derived units for volume can present some complications, particularly when we are converting units. Let's say that we've got this 10 centimeter cube. How many small cubes measuring 1 centimeter on each side are needed to construct a large cube measuring 10 centimeters on a side? The volume of a cube is whatever the edge length is, so 1 dimension, but cube it. And since the cube is 10 centimeters in each direction, we would need first, if we were building this out, we'd line up 10 cubes. And now we've got 1 dimension that's 10 centimeters, 10 of our cubes. We'd also have to line up 10 rows of these cubes. We have to stack up 10 rows of these cubes. We'll do that in orange. Go Giants, COS Giants. Because I had some people that were very confused last semester, because this is a running bit that I do. People that were very confused, they thought I was like either a football or baseball fan. It's not about those, it's about COS Giants, because that's one of our colors. Okay, back to the point. Right, so we'd have to stack up 10 of these rows tall to get 10 centimeters in the vertical direction. Since we had 10 wide, and now we've got 10 tall, we do 10 times 10, we've got 100 cubes. But then we need to stretch it out into space, depth as well. So we would add 10 rows of these 10 by 10 things. So we'd have 1,000 of these little cubes. We'd have 10 centimeters times 10 centimeters times 10 centimeters, or 10 cubes times 10 cubes times 10 cubes. We would end up with 1,000 centimeters cubed, or 1,000 cubes. One of the things that I'd like to point out here is that we treat our units like algebraic variables. So if you're multiplying 2 of them together, or in this case, multiplying 3 of them together, if you're multiplying 3 of them together, it's cubed. If it was 2, it would be squared. Like x times x gives us x squared. The same thing applies to our units. We can cube and square and whatever other exponents we might want to do to them. All right, some more units. So these are some common units and their equivalents. We've got different quantities, so distances of length. 1 kilometer is this many miles. We've got some different values for masses and different values for volumes. Table 1.3 might be something that you go back and reference. I sent in a print request to have some reference sheets that have a bunch of conversion factors on them printed. So I'll have those for you hopefully next week in class on Wednesday, probably, because they'll get them to me maybe Monday or Friday if we're lucky. One important note to point out here is that 1 cubic centimeter is equal to 1 milliliter. And another version of saying cubic centimeter, if I can write correctly, cubic starts with what letter? C. Centimeter also starts with what letter? C. So we could shorten that. CCs. And CCs often show up if we're talking about the engine displacement of motorcycles. Think Mario Kart. The speed that you're racing in Mario Kart, cubic centimeters, that's the size of your engine in Mario Kart. So cubic centimeters are the same as cm to the 3, or cc's, and it's also the same as milliliters. On trucks and other like larger automobiles, usually we measure engine displacement in terms of liters rather than cubic centimeters, but motorcycles often cc's. And then I'm getting tired of lecturing, so we'll stop after this slide probably. So density is also a derived unit. Density, often shortened to D, is a ratio. What's a ratio?
It's a part of.
Ratio means basically divide. So when I see ratio, I think we're dividing something or we're making a fraction, and it's a ratio of mass to volume. Our formula, density equals mass over volume. This would be a good one to know. And you'll also want to be able to rearrange this to solve for volume or to solve for mass. Mass is often going to be in something like grams. Volume will often be something like milliliters or cubic centimeters. Sometimes when you look stuff up, like if you're like, hey, what's the density of this object? Google, at least pre-AI summary, would spit out like kilograms per cubic meter, which is just a factor of 1,000 different from grams per milliliter, but is still like annoying. It's like, just give me the grams per milliliter, because that's what I care about as a chemist. Levy. Density is a physical property. It does depend on temperature. So as you heat things up, maybe you know this, when you heat stuff up, it expands slightly. When you cool things down, it compresses slightly. So density depends a little bit on temperature. Generally, we're not going to be concerned with changes in density. There's one trick, one fun trick that, arguably fun, that some students like to use for the density equation, so I'm going to show it to you. And it's this triangle or pyramid method. I'm not selling anything, I promise. So we're going to make a little triangle. And we've got 3 segments in our triangle. We're going to put density in the bottom left corner. We're going to put mass in the top. We're going to put volume in the bottom right. This works for this equation. There's one other equation that we'll come to later that's the same form that this also works for. And what's cool about this is if you don't like doing algebra, you can skip all of the algebra. This tells you how to do the algebra. So for example, let's say that I want to solve for, basically find, volume from mass and density. We could take d equals m over v and rearrange it so that the volume is on top by swapping it with the density, and we would get a value. If we don't like algebra, though, that's not very fun for us. So instead, what we're finding is volume. So we're going to cover up the volume. Pretend like it's not there. Pretend like it's not just over my hand. How are the other two things related?
Mass over density.
Mass over density. So you cover up the thing that you're trying to find. You look at the other two things. Volume equals mass over density. So we cover that up. Volume equals how the two things are related. Mass over density. That is the correct solve for volume. If you do it the algebra way, you multiply both sides by volume. You get volume times density equals mass. And then you divide both sides by density to get volume equals mass over density. Or maybe you're really good at algebra, you do it in one step. But what I'm showing you here is that you get the same answer if you use the little triangle method versus if you do the algebra way. So some of you, if you're not so algebraically inclined, may choose to use this method instead. Any questions about anything at all? Cool, we will stop there and pick up here on Monday.